Hey, you guys, we are going to learn about the correlation coefficient in this video. But before we can do that, we need to set up our graphing calculator. So get your graphing calculator out right now. And if you still don't have one, make sure you contact me and I can get you one. Okay, let's get going. So we're on our home screen of our graphing calculator. What we're going to do is we're going to hit the second button. Okay, so do that now. Then we're going to go to 0 where it has the catalog. Now what I want to do is I want to get to the diagnostic. So that's the D button you can see right here, D. So I'm going to hit that. Okay, so I'm at the D part. And I'm going to scroll down right now. Okay, and I see diagnostic on. So what have I done so far in case I went too fast for you? Hit second, 0, and then find the D letter and hit that. Now arrow down where you see diagnostic on, hit enter one more time, and we're good to go. Okay, we're good to go. Okay, so here was our issue from the last video. I talked about this oval test, and I know that's going to be uncomfortable for some of you because you're like, well, how thin should the oval be or whatever? And here's another catch. The scale and how you scale things, that can affect how thin or thick your oval is as well. Okay, so what we need is we need something a little more concrete to help us decide how strong the relationship is. And that's called the correlation coefficient. And what is that correlation coefficient? That is actually called R, okay? And what R does, that correlation coefficient, it tells us the direction and the strength of a linear relationship. Okay, two things, the direction and the strength. Well, how is it calculated? Let's look at this right here. This is kind of crazy, right? So what happens is we look at all of our X values, okay? The explanatory variable. So what we would do is we'd look at all of these right here. We would find the mean and the standard deviation. And then we would find the z-scores for each observation, okay? And then what we would do with those z-scores is we would add them all up. We would do the same for the y values. So we would go ahead and we'd find the mean and the standard deviation of the response variable. Then we'd find the z-score for each observation, and we would add it all up. And then we'd multiply those sums together. And finally, we would divide by n minus 1. N is the number of pairs that we have, or our sample size, how many runners we had. Divide that by n minus 1. Well, that's a lot to do. So we're not going to do that, but I do want you to know how it's calculated in the calculator. So we're going to go to our calculator right now, and we're going to do that together. Okay, we're going to figure out how to calculate it. So let me move this around a little bit so we can see it a little bit better. What I want to do right now, okay, is I want to enter the sprint time in my stat editor in L1, and I want to do my long jump distance time in L2, okay? So let's do that now. Well, how do I get to L1 and L2? Here's your reminder. Go to stat, hit enter on edit, scroll up to L1 and clear it. Do not delete it or it will be gone, and I can show you how to get that back, not a problem, okay? I'll do that at the end of the video if you accidentally do that, okay? And then go up to L2 and hit clear and enter. So we're gonna go ahead and we're gonna enter these times, okay? So I have 5.41, okay, enter, 5.05, oops, I already did 5.05. So what I'm gonna do right now is just to save us time on the video, I'm going to pause the video and I'm going to go ahead and I'm going to enter all of these in L1 and all of these in L2. You do that too, and we'll meet back. Okay, guys, so we should have the explanatory variable in L1, the response variable in L2, and just a friendly reminder, what is that explanatory variable? That was from the previous video. The explanatory variable is the variable we think influences the response or explains a change in the response. So we are saying that the sprint time is explaining how far we can jump, or it's influencing how far we can jump. Okay, that's what's the explanatory variable. And the response is the result. Okay, so that's what the result from that explanatory variable changing. Okay, so let's move on. What are we doing right now? We're calculating the correlation coefficient, and that's going to give us a more concrete way to describe the strength of that association. So now once we have it in L1, L2, we go to stat again. We arrow over to calculate. Now what we're going to do is we're going to go to this number 8 right here, lin reg, which means linear regression, A plus BX. Please note that there is a number 4 as well. That's not wrong, but I will always do number 8 because that's a standard textbook. We'll use number 8. So I want to stay consistent with that when and if you go on to further statistics. Okay, so you're comfortable with that and that's consistent for you. So I'm going to go down to number 8, or I can hit 8, right? Now, if you have the old calculator, that's okay. Bear with me and we'll get you there. Lin reg, we have our X list is L1, our Y list is L2. This says store the regression equation. What we could do is we could store it in Y1 if we wanted, but we don't need to. Okay. And here we go. We have Y equals A plus BX. So you'll notice I have my A here. That's my y-intercept. My b, that's my slope. We're going to save that for a different day in a different video. We have r squared. You're going to learn about what r squared is as well. But today, all we care about is our r, our correlation coefficient. We have now calculated that correlation coefficient. R equals negative 0.7518. Okay, first thing you accomplished, you calculated that correlation coefficient. But you know, in AP Stats, they want to know that you are more than just a number cruncher, that you can actually interpret the correlation coefficient as well. This must be memorized. I call it a note card type thing. You have to have this memorized, okay? The correlation coefficient, how do I interpret it? What I'm going to do right now is I'm going to actually give you the interpretation in context of what we're doing, and then I'll talk you through it. How would it change for a different type of problem? So remember I talked about what correlation coefficient is? It is your direction and your strength. So you can see because it's a negative number here, that's telling us, hey, we have a negative relationship. And then our strength, how strong it is, okay? 0.7518, what does that mean? Well, I have a little number line for you here. Oops, and it's not there. Okay, so I have a number line right here for you, right? And we're going from -1 to 1. So that's one thing you need to learn right away. A correlation coefficient, R, will always be between -1 and 1, inclusive, okay? If we have a correlation coefficient of 1 or -1, we have a perfect line. What is the difference? Okay, so that means our scatter plot is a perfect line. What is the difference? 1 is positive, so that means we have a positive association, right? Because correlation tells us direction and strength. -1 then just means we have a negative line. Okay, so what's kind of the standard? This is the hard thing. There's no textbook that says always 0.9 to 1 is very strong. Always from here to here is moderately strong, so on and so forth. So it is up to us to decide, okay? And what I will tell you again is the College Board does not try to trick you. My guess, if they're going to give you a correlation coefficient, it's either going to be around the 0.9 range or it's going to be around the 0.2, 0.3 range. It's going to be pretty strong or not strong at all, because in here, the water is a little bit muddy, okay? It's hard, it's thick, it's hard to know. Okay, so let's write some things down. First thing that we know, well, over here, any number from 0 to 1, what do we know? We know we have a positive association. Okay, and then any number from 0 to -1, that means we have a negative relationship, right? So a negative association. What if it's 0, which won't happen, okay? If it's 0, there's no relationship. Okay, next, how do I decide what is a strong relationship? I like to use like 0.9 as the cutoff to say, hey, if I have anything from 0.9 to 1, I have a very strong relationship. So this area right here, I'm going to say is very strong. If I go to my calculator and I calculate a correlation of R equals anywhere from 0.9 to 1, I'm saying that I have a very strong relationship. That would be the same for a negative 0.9 to negative 1. This region right here, anywhere there, I'm also going to say that that is, give me a second. Very strong. Well, we didn't have that, you guys. We had what, negative 0.74. So what would we say there? So right here now I have 0.9. This is 0.7 to 0.9. I like to say anywhere from 0.7 to 0.9, this region, okay? I call this strong. And I do the same for that negative 0.7 to negative 0.9. So that's this region right here. Okay, now then we have, some middle ground here. Okay, so I have 0.6, or let's go over on the positives. I like positives better. I have 0.3, let's see, so I have 0.1, 2, 3, 0.4, 0.5, 0.6, 0.7. This region here, okay, let's use a different color. I call this my moderate section. And whether it's moderately strong or moderately weak is dependent on which side of 0.5 are we on. Okay, so let's write this. So if I calculate something like 0.58, 0.6, 0.68, I'm going to say that's moderately strong. Whereas I calculate like 0.38, 0.4, 0.48, I'm going to call this area right here moderately weak. Why? Because I talk about anything from, let's see here, -1. Negative 0.3 is right here. I talk about anything in this region as being a weak relationship, okay? And the same is over here, you guys, okay? So from negative 0.7 to negative 0.3, right? I'm gonna use this negative 0.5 as kind of my guidance. If I'm over on this region right here, guys, I'm calling this moderately strong. But if I'm gonna have like a negative 0.4, I'm calling it moderately weak, okay? So anywhere in this region, we're saying we have a weak relationship. Now, this is our cutoffs to help us decide. We don't have to do that oval test anymore. We don't have to say how skinny it is, right? So some things you need to know about your correlation coefficient. Again, it's always going to go from -1 to 1. There are no units with it. It is also not resistant to outliers, okay? It's affected by outliers. Sorry, guys, my son just walked into the room, so he needed help with his distance learning, okay? All right, so again, like I said, there's no units on your correlation coefficient. We are going to round to 4 decimal places. It's always between -1 and 1. It is not resistant to outliers, which means it's influenced by outliers. If I have a nice thin oval, right? And then all of a sudden an outlier comes in, that oval's thickening, okay? So now that's going to weaken my relationship. But it is also not affected by changing units. If I would go back to my plot here and measure in not seconds, but milliseconds, okay? And not, what do we do, yards? I don't know where it went. Yards, but feet, okay? That relationship does not change. So it is not affected by changing units. The relationship, that R, is going to remain the same. Finally, we need to be able to interpret it, okay? So let's go ahead and do that now based off of that number line there, -0.7518. Let's look at that number line again and decide how strong is our relationship. Looking at the number line, you can see -0.75, I think it was, or 74 something, is right about right there, which means we have a strong relationship. Okay, so here we go. Interpreting it, write it down, okay? And then I'm going to talk you through it. So pause the video right now and write what I have down. Now let's talk about what it means, okay? R equals negative 0.7518 suggests that there is a strong, okay? We're talking about direction and strength here. So strong, negative. So that right there, that strong talked about the strength. The direction, the negative talked about the direction. We need those two things in these first two blanks. It doesn't matter the order. You could have said a negative strong. It doesn't matter the order, okay? R equals negative 0.75 suggests there is a strong negative linear relationship. Correlation coefficient only works with a with a linear relationship. We do not use correlation coefficient to describe a curved relationship, okay? Only a linear relationship. The linear relationship between sprint time and jump distance, okay? Please star this in your notes. You're going to use this template every single time. So you're basically just filling in the blanks. This first blank will always go the value of the correlation coefficient. These second two blanks will always give us, okay, the direction and the strength. So I did the strength first, doesn't matter. How do I know what that strength is going to be? That strength, I'm going to look at that number line that I drew in my notes, okay, that we just did together. So we have the strength and we have the direction. Of the linear relationship between this blank will always be our x variable in context, okay? So our x variable was sprint time, and our y variable here will be in the second blank, which in this context was jump distance. All right, guys, we're done. What should we have learned? Hey, we need something more concrete to describe the direction and the strength of the relationship. That is your correlation coefficient. We should know how to calculate it, okay? And we should know how to interpret it. And we can interpret that strength based off of this number line, okay, that we drew together. We should remember these facts about correlation coefficient and then how to interpret it in context. Have a great day, you guys. Thanks for joining me.